Something is wrong with Saturn. Not wrong in the way a machine malfunctions or a system degrades slowly into failure. Wrong in the way that makes planetary scientists stop mid-sentence during a conference presentation, re-examine data they have already reviewed a dozen times, and quietly wonder whether the models they have built over decades are missing something fundamental. The planet itself, the second largest in the solar system, a world so enormous that 760 Earths could fit inside its volume, is behaving in ways that no existing framework fully explains. The rings are disappearing. That single fact, confirmed by NASA scientists and published in peer-reviewed journals, carries a weight that the casual observer might underestimate. Saturn's rings are not a decoration. They are not a static feature of the outer solar system that has always been there and will always remain. They are an active, dynamic structure, hundreds of thousands of kilometers wide, yet in most places no thicker than a 10-story building, and they are being pulled into the planet at a rate that has genuinely alarmed the scientific community. The Cassini spacecraft, which spent 13 years in Saturn's orbit before making its final plunge into the planet's atmosphere in September 2017, measured the flow of ring material raining down onto Saturn. The numbers were staggering. Somewhere between 10,000 and 45,000 kilograms of ring material falls into Saturn every single second. Every second. To put that in terms a human mind can hold, that is the equivalent of a fully loaded 18-wheel freight truck, every second, dissolving into the planet's upper atmosphere without pause, without interruption, day after day, year after year. At that rate, the rings, a structure that stretches outward from Saturn's cloud tops to a distance comparable to the space between the Earth and the Moon, could be gone within 100 million years. In astronomical terms, that is nothing. The solar system is 4.5 billion years old. If the rings have existed since the beginning, they should have vanished long ago. And if they formed recently, then the word recently means something that should fundamentally change how we look at the solar system we think we know. But the ring loss is only one thread of a much larger and more unsettling puzzle. Saturn's atmosphere is changing in ways that models predicted imperfectly at best. The planet's north polar hexagon, a six-sided storm system so geometrically precise that for years after its discovery in the 1980s by the Voyager missions, some scientists genuinely struggled to accept that it was a natural phenomenon, has been shifting color. When Cassini arrived in the early 2000s, the hexagon was a deep blue. By the time the mission ended, it had turned golden. No one has produced a complete, peer-reviewed explanation for that color shift. The leading hypothesis involves sunlight-driven chemical changes in the upper atmosphere as Saturn moved through its seasonal cycle, but the details of the chemistry remain contested, and the precision of that color change, so vivid, so dramatic, still generates discussion at every major planetary science conference. Then there is the magnetic field. Saturn is the only planet in the solar system whose magnetic axis is aligned almost perfectly with its rotational axis. In every other magnetized planet, Earth, Jupiter, Uranus, Neptune, there is a measurable tilt between the magnetic pole and the geographic pole. On Earth, that tilt is about 11 degrees, which is why a compass does not point exactly toward the North Pole. On Jupiter, the offset is roughly 10 degrees. On Saturn, the offset is so small, less than 1/10 of a degree, that for years it resisted all standard measurements. This is deeply strange. The dynamo theory of planetary magnetism, which describes how a rotating electrically conducting fluid generates a magnetic field, explicitly predicts that a perfectly aligned magnetic field should not be stable over geological timescales. Something in Saturn's deep interior must be actively suppressing any measurable tilt. What that something is remains one of the most provocative open questions in planetary physics. Saturn sits roughly 1.4 billion kilometers from the Sun. Light, traveling at 300,000 kilometers per second, takes approximately 80 minutes to make that journey. When you look at Saturn through a telescope tonight, you are seeing the planet as it was an hour and 20 minutes ago. It is a world of crushing atmospheric pressure in its lower layers, with wind speeds at the equator exceeding 500 kilometers per hour. Its surface, If the word surface can even apply to a world that is predominantly gaseous and transitions gradually, without a hard boundary, into denser and denser layers, is not somewhere a human being could stand. The pressures at depth would compress any known material into forms that barely exist in laboratory conditions on Earth. Yet for all of that alien hostility, Saturn has been part of human awareness since antiquity. Ancient Babylonian astronomers tracked its slow path across the sky. Because Saturn takes approximately 29.5 Earth years to complete a single orbit around the Sun, ancient observers watched it as the slowest moving of all the visible planets, associating it with time, with age, with the long, slow turning of things. They had no way of knowing they were watching a world 9 times wider than Earth, a world with a gravitational pull so powerful that it has captured at least 146 moons, more confirmed moons than any other planet in the solar system. They had no way of knowing that the steady, pale yellow point of light they tracked through the constellations harbored in its rings more individual particles of ice and rock than there are grains of sand on every beach on Earth combined. Galileo Galilei first observed Saturn's rings in 1610, though his telescope was too primitive to resolve them as rings. He described Saturn as a triple-bodied object, a large central sphere flanked by 2 smaller bodies, and was baffled when, 2 years later, he looked again and the companions had vanished. He had been seeing the rings at 2 different angles. When Earth crossed Saturn's ring plane and the rings were viewed edge-on, they effectively disappeared from his instrument entirely. He never resolved the mystery himself. It fell to Christian Huygens in 1655 to correctly identify the structure as a flat ring surrounding the planet. For 350 years after Huygens, humanity observed Saturn's rings as a fixture of the solar system, as permanent as the planet itself. The idea that they might be temporary, geologically speaking, that we might be living in the narrow window of time when Saturn happens to have a spectacular ring system, was not seriously entertained until the data from Cassini forced the question into the open. And now that the question is open, it pulls everything else with it. If the rings are young, formed, according to some models, as recently as 100 million years ago, then what created them? A shattered moon? A captured comet torn apart by Saturn's tidal forces? And if something catastrophic happened in the outer solar system 100 million years ago, what else changed? What other signatures of that event are still embedded in the structure of the planet we have been watching for centuries, thinking we understood it? The ring reign continues. Right now, at this moment, material that has existed in Saturn's ring system for potentially millions of years is falling into the planet's atmosphere, ionizing, dissolving, becoming part of the gas giant itself. The rings are, in the most literal scientific sense, dying. And the reason they are dying, the full, complete, satisfying explanation that ties together the ring loss, the magnetic anomaly, the shifting hexagon, the missing thermal energy that scientists have measured radiating from Saturn's interior, does not yet exist. The Cassini spacecraft launched on October 15, 1997 from Cape Canaveral. It carried 12 scientific instruments, weighed nearly 6,000 kilograms fully fueled, and took nearly 7 years to reach Saturn. When it finally entered Saturn's orbit on July 1, 2004, it became humanity's most sophisticated eye ever pointed at the ringed planet. Nothing before it came close. Voyager 1 and Voyager 2 had flown past Saturn in 1980 and 1981 respectively, spending only hours in the planet's vicinity before continuing their outward trajectories toward interstellar space. Cassini would spend 13 years in orbit, executing 294 orbits around Saturn, flying through the ring gaps, skimming the cloud tops, threading the needle between ring bands with a precision that still seems improbable. The data it returned fills entire server archives at NASA's Jet Propulsion Laboratory. Scientists are still publishing new findings from it today. And the deeper they dig into that archive, the more the questions multiply. The ring reign was the first shock. Cassini's ion and neutral mass spectrometer, an instrument designed to identify and measure the chemical composition of particles in Saturn's upper atmosphere, detected water, organic compounds, silicate particles, and carbon dioxide streaming downward from the rings at a rate nobody had anticipated. The data was so unexpected that the team spent years validating it, running checks against alternative explanations, ensuring that the instrument itself wasn't producing artifacts. It wasn't. The rings are actively losing mass to the planet. The scientific term for this process is ring rain, a name that understates what it actually represents: the structural dissolution of one of the most visually dominant features in the entire solar system. What drives this dissolution? The answer involves one of the most fundamental forces in physics, operating at a scale that stretches comprehension. Saturn's magnetic field, that near perfectly aligned anomaly discussed in every planetary science journal for the past 4 decades, intersects with the charged particles that populate the ring plane. The rings are not simply ice and rock floating in neutral space. They exist within Saturn's magnetosphere, a region of space dominated by the planet's magnetic influence that extends millions of kilometers in every direction. Within this magnetosphere, ultraviolet radiation from the sun and energetic electrons continuously bombard ring particles, stripping electrons from water molecules and leaving behind positively charged ions. These ions, now electrically coupled to Saturn's magnetic field lines, are pulled along those field lines directly into the planet's atmosphere. Gravity does the rest for the neutral particles. The result is a continuous bidirectional drain: charged particles guided by magnetism, neutral particles dragged by gravity. Both pathways lead to the same destination. The rate of this drain is not constant. Cassini measured variations tied to Saturn's seasons. The planet tilts at roughly 26.5 degrees relative to its orbital plane, almost identical to Earth's axial tilt of 23.5 degrees. Saturn's year lasts approximately 29.5 Earth years, which means each of its seasons stretches across roughly 7 Earth years. As the planet's north pole tips toward the sun during northern summer, the geometry of the ring-sun interaction changes, altering how much ultraviolet radiation reaches the ring plane and therefore how rapidly ring particles become ionized. More ionization means more ring rain. The rings themselves pulse with the rhythm of Saturn's slow seasonal clock. But the rings are not a uniform structure. That is perhaps the most important thing to understand about them, and it is also the thing most commonly misrepresented in popular descriptions of the planet. The ring system is divided into distinct bands, each with different compositions, densities, and ages. The A ring and the B ring, the two brightest bands clearly visible through even a modest amateur telescope, are primarily composed of water ice particles ranging in size from microscopic grains to chunks the size of a house. The B ring alone contains an estimated 15 to 20 times more mass than the A ring, despite occupying a similar visual footprint. The C ring, closer to the planet, is darker and thinner. The D ring, the innermost ring, is so faint it was not even confirmed until the Voyager missions. Beyond the A ring sits the F ring, a narrow, braided structure that 2 small moons, Prometheus and Pandora, actively shepherd through gravitational perturbations, preventing it from spreading and dispersing. Each time Prometheus swings close to the F ring during its orbit, which happens approximately every 17 Earth hours, it carves a dark channel into the ring material, a gravitational wake that persists for weeks before fading back into the general structure. The outer rings extend even further. The E ring, fed entirely by material ejected from the geysers of Enceladus, Saturn's small ice moon with a confirmed liquid water ocean beneath its frozen surface, spreads across a vast swath of space beyond the main ring system. Enceladus ejects roughly 200 kilograms of water vapor and ice particles per second from fractures in its south polar region. That material fans outward, some of it falling back onto the moon, but a significant fraction escaping into Saturn's magnetosphere and supplying the E ring with fresh material continuously. Without Enceladus, the E ring would vanish within decades. The fact that one of Saturn's moons is actively feeding one of its ring bands raises a question that planetary scientists have been wrestling with for years. Could the rings themselves have originated from a moon? Not Enceladus. Its contribution is modest compared to the total mass of the ring system. But a larger moon. A moon the size of Mimas, perhaps, or larger. The hypothesis, developed in detail by researchers including Mattia Cook at the SETI Institute and Luke Duns at the Southwest Research Institute, proposes that early in Saturn's history, a large icy moon, or possibly several, spiraled inward due to gravitational interactions with the planet, and was torn apart by tidal forces as it crossed the Roche limit. The Roche limit is the distance from a planet within which tidal forces overcome the self-gravity of an orbiting body. Inside this boundary, any object held together primarily by its own gravity, rather than by chemical or structural bonds, will be shredded. For Saturn, the Roche limit lies at roughly 87,000 kilometers from the planet's center. The main ring system extends from approximately 67,000 to 140,000 kilometers from the center, placing it almost entirely within or near this zone of tidal destruction. A moon entering this region would not survive. Its constituent ice and rock would be spread into a disk, and that disk, given enough time, would evolve under the influence of collisions, radiation pressure, and gravitational resonances into something resembling what Cassini observed. The timing suggested by the ring's relatively low contamination level, the ratio of non-ice material mixed into the ring particles is surprisingly small, indicating the rings have not been collecting dust and debris for billions of years, points toward formation sometime in the last 100 to 400 million years. That window corresponds to the Cretaceous period on Earth. While non-avian dinosaurs were crossing Cretaceous floodplains, Saturn may have been acquiring its iconic ring system for the first time. That realization sits uneasily against a deeper question. If the rings formed that recently, and if they are already losing mass at the rate Cassini measured, then their total lifespan is geologically brief. 100 million years to form, 100 million years to disappear. The solar system is 4.5 billion years old. The probability that any civilization capable of looking up at the night sky would exist during the narrow window when Saturn has prominent rings is remarkably low. Yet here we are, looking up. Whether that is coincidence or something that deserves reflection is a question that physics alone cannot resolve. The mystery does not stop at the rings. Beneath those rings, beneath the visible cloud layers that Cassini photographed in extraordinary detail, Saturn's interior holds an anomaly that has resisted every attempt at a clean explanation. The planet radiates roughly twice as much energy as it receives from the Sun. Jupiter does the same. For Jupiter, the accepted explanation involves the Kelvin-Helmholtz mechanism. Jupiter is still slowly contracting under its own gravity, and that contraction releases gravitational potential energy as heat. The planet is, in a very real sense, still cooling down from its formation 4.5 billion years ago. The same mechanism was assumed to explain Saturn's excess heat. The mathematics applied to a planet of Saturn's mass predicted a certain rate of contraction and a corresponding heat output. When scientists compared that prediction to actual measurements, the numbers did not match. Saturn radiates significantly more heat than simple gravitational contraction can account for. Something else is generating heat inside Saturn. Helium rain. The phrase sounds almost gentle. It is not. Deep inside Saturn, at pressures that no material on Earth's surface ever experiences, helium atoms are separating from hydrogen and falling inward toward the planet's core in droplets. A process as relentless and consequential as anything in planetary science, and one that took decades of theoretical work to even propose, let alone begin to verify. To understand why this happens, the interior of Saturn must be understood not as a static, layered structure, like an onion sliced cleanly in cross-section, but as an active, dynamic system where pressure, temperature, and chemistry interact in ways that have no analog in everyday human experience. At Saturn's cloud tops, the atmospheric pressure is roughly comparable to what a human diver experiences at a depth of about 10 meters in the ocean. Manageable. Familiar. Descend further into Saturn, not physically but conceptually, following the mathematics, and the pressure climbs with extraordinary speed. At a depth of a few thousand kilometers, the pressure exceeds anything achievable in most laboratory settings on Earth. The hydrogen gas that makes up the bulk of Saturn's outer atmosphere begins to behave in ways that the word gas no longer adequately describes. At pressures exceeding roughly 1 million times Earth's atmospheric pressure, hydrogen undergoes a phase transition into a state called metallic hydrogen. In this state, the electrons that normally orbit hydrogen nuclei are no longer bound to individual atoms. They flow freely through the material, the way electrons flow through a copper wire. Metallic hydrogen is, in a real and measurable sense, an electrical conductor, and it is the movement of these free electrons through Saturn's rotating interior that generates the planet's magnetic field. The same mechanism operates inside Jupiter, inside the ice giants Uranus and Neptune in modified forms, and, to a different degree, inside the Earth itself, where liquid iron in the outer core performs an analogous role. But Saturn's metallic hydrogen region is not pure. It contains helium. And this is where the physics becomes genuinely strange. In the outermost layers of Saturn's interior, hydrogen and helium mix relatively freely, much as two miscible liquids blend together at room temperature. But as depth increases and pressure builds past a critical threshold, the thermodynamic conditions change. The mixture of hydrogen and helium crosses what physicists call a miscibility boundary, a point where the two elements become less willing to stay blended and begin to separate, the way oil and water separate when a salad dressing sits undisturbed. Helium, being denser than the surrounding hydrogen under these extreme conditions, begins to condense into droplets and sink. Those droplets fall toward deeper, hotter regions of the planet's interior. As they fall, they release gravitational potential energy. That energy converts to heat. This is the missing heat source. The theoretical framework for helium rain was developed primarily by David Stevenson and Edwin Salpeter in the late 1970s. Their work predicted that both Jupiter and Saturn should exhibit this process, but that Saturn, being smaller, cooler, and therefore having crossed the helium miscibility boundary earlier in its history, should show a more advanced stage of helium separation than Jupiter. One observable consequence of this prediction: Saturn's upper atmosphere should be depleted in helium relative to the primordial solar composition, because helium has been raining inward for billions of years, leaving the outer layers progressively helium-poor. Measurements by Voyager 2 confirmed this depletion. Saturn's atmosphere contains roughly 11 to 12% helium by mass, compared to approximately 24% in the Sun and the primordial solar nebula from which the planets formed. Jupiter's helium abundance is closer to 24%. The difference is exactly what the helium rain hypothesis predicts. The numbers align. The mechanism is physically coherent. The Voyager data corroborates it. Yet confirmed remains too strong a word for the scientific community's current position. The interior of Saturn cannot be observed directly. No instrument has ever measured conditions below the cloud tops. Every number assigned to Saturn's deep interior is inferred, derived from models constrained by gravity measurements, seismological data, and theoretical equations of state for hydrogen-helium mixtures at extreme pressures. The laboratory generation of metallic hydrogen has only been achieved in microsecond bursts using shock compression experiments. The conditions inside Saturn persist continuously for billions of years. Whether laboratory microseconds fully capture the physics of planetary interiors that have evolved across geological time is a question that remains unresolved. Saturn's gravity itself carries information about its interior. The way the planet's gravitational field deviates from a perfect sphere, encoded in what physicists call gravitational harmonics, represented by the coefficients J2, J4, J6 in the mathematics of gravitational potential, constrains the distribution of mass within the planet. Cassini spent the final phase of its mission, called the Grand Finale, executing 22 orbits that passed between Saturn's innermost ring and its cloud tops, a gap of roughly 2,000 kilometers. No spacecraft had ever flown through that region. These orbits allowed Cassini's radioscience instruments to measure Saturn's gravitational field with unprecedented precision. The results, published in Science in 2019, revealed something unexpected. The gravitational harmonics could not be explained by a simple two-layer model of a rocky core surrounded by a fluid envelope. The data demanded a more complex interior structure, a fuzzy core in the terminology used by the research team, where the rocky and icy central region grades diffusely into the surrounding metallic hydrogen rather than having a sharp, well-defined boundary. This fuzzy core extends to roughly 60% of Saturn's total radius. In physical terms, that means the transition zone between what might loosely be called Saturn's core and its outer envelope spans a distance of approximately 35,000 kilometers, larger than 3 Earth diameters placed side by side. The fuzziness itself is thought to be a consequence of Saturn's formation history, a period when rock, ice, and gas were accreting simultaneously and never fully differentiated into clean, layered zones. 4.5 billion years of slow mixing, driven by fluid instabilities in the interior, has blurred the boundaries further. The fuzzy core also carries implications for Saturn's rings. If Saturn's interior is more diffuse than previously assumed, its moment of inertia, a quantity describing how mass is distributed relative to the rotation axis, differs from earlier estimates. Moment of inertia directly affects the rate at which a planet's gravitational resonances interact with orbiting objects. The rings of Saturn are not passive. Certain ring structures are sculpted by orbital resonances with Saturn's moons, positions in the rings where a particle's orbital period is a simple fraction of a moon's orbital period. At these resonance locations, repeated gravitational tugs accumulate and push ring material away, creating the gaps and wave structures that Cassini photographed in extraordinary detail. If Saturn's interior mass distribution is different from what the models assumed, every resonance calculation built on those assumptions needs to be revised. The planet is more connected than it appears. Its atmosphere, its rings, its magnetic field, and its deep interior are not independent systems. They are coupled. Changes in one propagate through the others along pathways that scientists are only beginning to map. Ring seismology made this coupling visible in a way that nothing else had. In 2013, Matthew Hedman and Philip Nicholson published an analysis of spiral density waves in Saturn's C ring, subtle repeating wave patterns in the ring's density measured by Cassini's imaging instruments. These waves, they found, were not being driven by any known moon. They were being driven by oscillations in Saturn's interior itself. Saturn, like the Sun and like Earth, rings like a bell. Its interior oscillates in normal modes, standing waves of pressure and density, and those oscillations perturb the planet's gravitational field in a periodic way. Ring particles in resonance with these oscillations are pushed into the wave patterns Cassini observed. The rings, in other words, are a seismograph. By reading the spiral waves in Saturn's C ring, scientists have inferred the frequencies and properties of vibrations occurring tens of thousands of kilometers below the cloud tops, in regions forever inaccessible to direct measurement. This technique, called chronoseismology, from Kronos, the Greek name for the deity associated with Saturn, is still in its infancy. Only a fraction of the wave structures in Saturn's rings have been analyzed. The full catalog of Saturn's interior oscillation modes remains incomplete. Each new mode identified is a new constraint on interior models, a new piece of data that any successful theory of Saturn's structure must eventually account for. The planet vibrates, the rings record it, and the record so far is only partially read. For most of the 20th century, Saturn's rotation rate was considered a solved problem. Voyager 1 measured it in 1980 by tracking the periodicity of radio emissions generated by Saturn's magnetosphere, a pulsing radio signal that, by analogy with Jupiter, was assumed to be locked to the planet's deep interior rotation. The period Voyager measured was 10 hours, 39 minutes, and 22.5 seconds. That number entered the textbooks. It was cited in thousands of papers. It became the foundation upon which calculations of Saturn's internal structure, wind speeds, and atmospheric dynamics were built. For 25 years, no one questioned it seriously. Then Cassini arrived, and the number was wrong. Not slightly wrong. Not wrong in the way that a measurement refined by better instruments produces a marginally adjusted value. Wrong in a way that defied straightforward explanation. Cassini's radio and plasma wave science instrument, measuring the same magnetospheric radio pulsations that Voyager had measured, returned a period of 10 hours, 45 minutes, and 45 seconds. A difference of more than 6 minutes compared to Voyager's value, 6 minutes per rotation. For a planet that completes a full rotation in roughly 10.5 hours, a 6-minute discrepancy is not a rounding error. It is a fundamental inconsistency that demands explanation. The immediate hypothesis was instrument error. It wasn't. The data was clean, reproducible, and internally consistent across multiple Cassini instruments and multiple years of observation. A second hypothesis proposed that Saturn's rotation rate had genuinely changed between the Voyager flyby in 1980 and Cassini's arrival in 2004. A planet's deep interior rotation rate does not change by 6 minutes in 24 years. The timescales of planetary interior dynamics operate over millions to billions of years, not decades. That hypothesis collapsed under its own implausibility. A third possibility emerged, and it was the one that ultimately held up under scrutiny. The radio pulsation period measured by both Voyager and Cassini was never the rotation rate of Saturn's interior in the first place. Something in Saturn's magnetosphere was modulating the radio emissions, imposing a period on them that reflected atmospheric or magnetospheric dynamics rather than the solid body rotation of the deep interior. And that something was changing over time, which is why the period measured in 1980 differed from the period measured in 2004. This was a deeply unsettling realization. It meant that planetary scientists had spent 25 years using a number that did not mean what they thought it meant. Every calculation of Saturn's wind speeds, derived by comparing observed cloud motion to the assumed interior rotation rate, needed to be reconsidered. Every model of the planet's interior that incorporated the Voyager rotation period as a constraint needed to be re-examined. The planet that had seemed well characterized was, in a specific and important sense, still spinning at an unknown rate. The source of the modulation was traced to Saturn's ionosphere, the upper layer of the atmosphere where solar radiation ionizes gas molecules, and specifically to asymmetric features in the ionosphere that rotate around the planet and impose their periodicity on the magnetic field configuration. Both Saturn's northern and southern hemispheres produce these modulations, and they operate at slightly different periods, both of which shift over time with the planet's seasons. The northern and southern periods converge and diverge in a cycle tied to Saturn's orbital period around the Sun. This was not in any model. No theory predicted it. It emerged entirely from the data. Cassini's grand finale orbits in 2017 finally provided a path toward resolving the true rotation rate. By flying between the rings and the planet and measuring the gravitational field with extreme precision, the mission's radio science team was able to constrain Saturn's moment of inertia independently of any rotation period derived from radio emissions. Combined with models of atmospheric wind dynamics, this yielded a best estimate of Saturn's internal rotation period of approximately 10 hours, 33 minutes, and 38 seconds, a value shorter than both the Voyager and Cassini radio-derived periods. The winds in Saturn's upper atmosphere, blowing at speeds of up to 500 kilometers per hour relative to this internal rotation rate, are therefore even faster than previously calculated. They represent one of the most powerful sustained atmospheric circulation systems in the solar system. The wind structure itself conceals another layer of discovery. Cassini's gravity measurements during the grand finale revealed that Saturn's winds do not merely skim the surface of the atmosphere, they penetrate deep. The gravitational harmonics measured during those final orbits could only be reproduced in models if the atmospheric winds extended downward to a depth of approximately 9,000 kilometers below the visible cloud tops. 9,000 kilometers. The distance from the Earth's surface to its center is just over 6,000 kilometers. Saturn's weather layer is deeper than the entire radius of the Earth. At 9,000 kilometers depth, the electrical conductivity of the hydrogen rises enough that the magnetic field begins to strongly resist further wind penetration. The field lines act as a brake, coupling the deep atmosphere to the interior and preventing the wind patterns from extending further inward. This depth, called the magnetic braking depth, marks the lower boundary of what can reasonably be called Saturn's weather system. Below it, the dynamics are dominated by the planet's interior rather than by solar energy deposited at the cloud tops. The boundary is not sharp, it is a transition zone spanning hundreds of kilometers. But its existence confirms that Saturn's atmosphere and interior are in direct mechanical communication across a depth range that dwarfs anything in Earth's experience. The storms that periodically erupt across Saturn's surface make this communication brutally visible. Saturn experiences what planetary scientists call great white spots, massive convective storm systems that appear at irregular intervals, historically observed roughly once per Saturnian year, approximately every 30 Earth years. The most recent Great White Spot erupted in December 2010 and was observed in extraordinary detail by Cassini. The storm began as a bright white spot in Saturn's northern hemisphere and within weeks had spread into a convective complex that encircled the entire planet at that latitude. A storm band stretching across a circumference of hundreds of thousands of kilometers. It persisted for months before the head of the storm collided with its own tail, a phenomenon with no precise analog in Earth meteorology, and finally dissipated. The energy source for great white spots is internal. Unlike hurricanes on Earth, which are powered by warm ocean water evaporating at the surface, Saturn has no surface and receives comparatively little solar energy at its distance from the Sun. The convective eruptions are driven by heat rising from the planet's interior, the same excess heat that helium rain and residual gravitational contraction generate, breaking through a stable atmospheric layer that suppresses convection for years or decades until the accumulated energy overwhelms it. The 2010 storm released so much energy that it temporarily disrupted Saturn's global thermal emission pattern, measurable by Cassini's instruments as anomalies in the planet's infrared brightness. Within the storm system, lightning was detected, radiostatic bursts of extraordinary intensity, millions of times more powerful than a typical lightning bolt on Earth. Cassini's radio instruments recorded these discharges as electrostatic discharges, and the 2010 storm produced the most powerful and sustained series of Saturnian lightning ever measured by any spacecraft. The lightning was not a peripheral feature of the storm. It was an indicator of the convective engine at work, the violent mixing of gases at different temperatures and compositions as interior heat drove plumes of material upward through the atmospheric layers. That interior heat, generated by helium rain and gravitational contraction, had been building beneath the stable atmospheric cap for years before the 2010 eruption. The storm was, in one sense, the planet exhaling, releasing the accumulated pressure of its own slow internal evolution through a violent atmospheric convulsion. The event lasted 7 months. It encircled the planet. And it was triggered entirely by the physics happening in a region of Saturn's interior where no instrument has ever directly measured anything. The planet's interior speaks, the atmosphere listens, the rings record the conversation. And every time scientists believe they have closed a chapter in Saturn's story, the data opens another. On September 15, 2017, the Cassini spacecraft ceased to exist, not in the way that machines wear out or signals fade to silence across interplanetary distances. Cassini ended on a precise schedule, by deliberate design, entering Saturn's atmosphere at a speed of approximately 113,000 kilometers per hour, fast enough to circle the Earth 3 times in a single minute, and was destroyed by aerodynamic forces and atmospheric friction within minutes. The decision to terminate the mission this way was not arbitrary. Cassini had exhausted its maneuvering fuel. Without the ability to precisely control its trajectory, an unguided spacecraft might eventually collide with Enceladus or Titan, moons that Cassini itself had revealed as candidates for harboring liquid water and therefore candidates for harboring life. Contaminating those worlds with terrestrial microorganisms that had survived the journey from Earth was an outcome the scientific community was not willing to risk. Cassini was sent into the planet it had spent 13 years studying. In its final 22 orbits during the grand finale phase, Cassini flew closer to Saturn than any spacecraft in history. It passed through the gap between the innermost ring and the planet's upper atmosphere repeatedly, sampling the material in that region directly with its instruments. What those instruments found was unexpected in its detail and richness. The gap is not empty. It contains a thin but measurable population of particles: dust, complex organic molecules, water vapor, silica grains, flowing both inward from the rings toward the planet and outward from the planet's upper atmosphere into the ring plane. The two systems are in continuous material exchange. They always have been. Cassini was the first instrument sensitive enough to measure it directly. On the final orbit, Cassini's transmitter remained active as long as physically possible. The spacecraft's antenna was pointed toward Earth, maintaining a continuous data stream as it descended. Scientists at the Jet Propulsion Laboratory tracked the signal as it weakened and then, at 5:55 in the morning Pacific time on September 15th, went silent. The last data Cassini transmitted included atmospheric composition measurements from the uppermost layers of Saturn, direct, in situ chemical sampling of the planet's atmosphere. The first and so far only time any instrument has physically entered Saturn and measured what is there. The data showed water, molecular hydrogen, methane, carbon monoxide, carbon dioxide, and complex organic molecules at concentrations that confirmed and extended earlier remote sensing measurements. Then the signal ended, and Saturn continued, unchanged, indifferent, vast. The atmosphere Cassini entered and was destroyed by extends upward from the visible cloud tops for thousands of kilometers into a tenuous thermosphere. The outermost atmospheric layer before the boundary with space becomes essentially meaningless. Saturn's thermosphere is anomalously hot. Temperatures there reach between 300 and 500 degrees Kelvin, far warmer than solar heating at Saturn's distance from the Sun can account for. The Sun, at 1.4 billion kilometers from Saturn, delivers roughly 1% of the solar energy per square meter that it delivers at Earth's distance. It cannot explain the thermosphere temperatures. Something else heats it. The leading candidates are two mechanisms, both confirmed in part but neither fully quantified. The first is Joule heating, the dissipation of electrical energy as ionospheric currents interact with Saturn's magnetic field. The second, more dramatic, is the direct energy input from the ring rain. As charged ring particles spiral down Saturn's magnetic field lines into the upper atmosphere, they carry kinetic energy with them. That energy is deposited at specific latitudes, the magnetic footprints of the ring plane in the upper atmosphere, creating localized heating zones. Cassini's ultraviolet imaging spectrograph detected auroral emissions at these latitudes, confirming that the ring ionosphere interaction is a real energy transfer pathway. But the measured energy fluxes, when summed, still fall short of fully accounting for the observed thermosphere temperatures. The heating budget is not closed. Something in the accounting is still missing. Saturn's aurorae deserve their own attention. Like Earth's northern and southern lights, Saturn's aurorae are generated when energetic charged particles from the solar wind and from the magnetosphere are funneled along magnetic field lines into the upper atmosphere, where they collide with gas molecules and cause them to emit light. Saturn's auroral emissions are primarily in the ultraviolet, invisible to the naked human eye, and occur in a ring around each pole. The Hubble Space Telescope has imaged these auroral rings from Earth's orbit in ultraviolet light, and Cassini photographed them from close range over many years. Saturn's aurorae are not static. They pulse, brighten, and shift in response to changes in the solar wind pressure. When a coronal mass ejection from the Sun reaches Saturn, a burst of energetic plasma traveling at several hundred kilometers per second across 1.4 billion kilometers of interplanetary space, Saturn's aurorae flare in response within hours. The connection between a star and a planet across that distance, mediated by fields and particles that are invisible to any human sense, and manifesting as curtains of ultraviolet light rippling around a planet's poles, is the kind of physical reality that no metaphor adequately captures. The numbers must stand on their own. 1.4 billion kilometers, hours. The solar wind does not slow meaningfully across that distance. It arrives at Saturn carrying the memory of events on the solar surface, a memory written in particle velocities and magnetic field orientations, and Saturn responds. The magnetic field that makes this response possible remains, as established earlier, the deepest anomaly on the entire planet. In 2019, a team led by Michelle Dougherty at Imperial College London used the grand finale magnetometer data to place the tightest constraint ever achieved on Saturn's magnetic axial tilt, less than 0.01 degrees. For context, a tilt of 0.01 degrees corresponds to an offset between Saturn's magnetic pole and its geographic pole of less than 200 kilometers at the planet's surface. On a planet with a radius of 58,000 kilometers, that is a misalignment of less than 0.3% of the radius. No dynamo model has been able to stably maintain a tilt this small over the age of the solar system. The most plausible current hypothesis, proposed by Sabine Stanley at Johns Hopkins University and colleagues, involves a stably stratified layer of helium-depleted hydrogen just above the metallic hydrogen region, a layer that acts as an electromagnetic filter, smoothing out and suppressing any magnetic field components that are not aligned with the rotation axis. The tilt that exists is buried deep below the filtering layer, and what the outside of the planet sees is the filtered, symmetrized result. If this hypothesis is correct, Saturn's magnetic field is not showing its true face. The deep interior may harbor a tilted, complex dynamo that the filtering layer systematically erases from external view. Measuring the true deep field would require instruments inside that filtering layer. Instruments no current technology can deliver to that environment and survive. Titan enters this picture in its own right. Saturn's largest moon, larger than the planet Mercury, possessing a dense nitrogen atmosphere thicker in terms of surface pressure than Earth's own, interacts with Saturn's magnetosphere in a way that makes it a planetary system within a planetary system. Titan orbits Saturn at a distance of roughly 1.2 million kilometers, completing one orbit every 15.9 Earth days. It spends most of its orbital period inside Saturn's magnetosphere, where it is bathed in Saturn's magnetic field and in the plasma that populates that region. The interaction between Titan's ionosphere and Saturn's magnetospheric plasma creates a complex electromagnetic wake that stretches for hundreds of thousands of kilometers downstream of the moon's orbital motion. Cassini flew through that wake on multiple occasions and sampled it directly. The data revealed that Titan is losing atmospheric material continuously, stripped by the magnetospheric interaction, and injected into Saturn's magnetosphere as heavy organic ions. Over geological timescales, this loss has contributed to shaping Titan's atmosphere. The moon and the planet are chemically coupled across more than 1 million kilometers of space. Everything in the Saturn system interacts with everything else. The interior drives the atmosphere. The atmosphere feeds the magnetosphere. The magnetosphere sculpts the rings and strips material from the moons. The moons feed the rings and shape the outer ring structure. The rings heat the thermosphere and record the planet's internal vibrations. Saturn is not a planet with accessories. It is a system, integrated, dynamic, and still, in crucial ways, poorly understood. The Cassini mission answered hundreds of questions about Saturn. It generated thousands more. That is not a failure of science. It is exactly what science looks like when it is working. Saturn is currently 657 years old in human astronomical attention. That is how long it has been since Nicholas Copernicus was born, since the intellectual tradition that would eventually produce telescopes, spacecraft, and magnetometers first began displacing Earth from the center of the known universe. 657 years of increasingly sophisticated attention directed at a pale yellow point of light that moves slowly against the fixed stars, and the fundamental question of what is happening inside it remains open. The interior rotation rate was unknown until 2 years ago. The age of the rings is constrained to a range spanning 300 million years, a range wider than the entire Mesozoic era. The source of excess thermospheric heating is unmeasured. The mechanism sustaining a perfectly symmetric magnetic field across billions of years has no confirmed explanation. These are not peripheral details. They are the load-bearing questions of Saturnian science. What is known with high confidence is the following. The rings are young in geological terms and are actively disappearing. The planet's interior is not a cleanly layered structure, but a diffuse, fuzzy system that grades continuously between rocky core and gaseous envelope across a transition zone spanning tens of thousands of kilometers. The atmospheric winds penetrate to depths exceeding 9,000 kilometers, braked at the bottom by magnetic coupling to the interior. The magnetic field, generated somewhere in the metallic hydrogen region deep below the cloud tops, passes through a filtering layer that strips it of any measurable axial tilt before it reaches the surface. Helium is raining inward, releasing gravitational energy as heat, depleting the outer atmosphere of helium relative to the solar composition, and doing so at a rate that has been ongoing since early in the planet's history. The rings oscillate in response to the planet's internal vibrations. The moons and the rings exchange material with each other and with the planet's atmosphere continuously. Every one of these facts was either unknown or poorly constrained 30 years ago. The picture has changed radically within a single scientific generation. It will change again. The mission that will attempt to change it next is already defined. Dragonfly, NASA's rotorcraft lander, is scheduled to reach Titan in the 2030s. Not Saturn itself, but Saturn's largest moon, a world with prebiotic chemistry, liquid methane lakes, and an organic, rich atmosphere that some researchers have proposed as a potential environment for non-aqueous life chemistry. Dragonfly will not answer questions about Saturn's interior, but it will characterize Titan's surface chemistry in unprecedented detail, adding another data point to the question of how the Saturn system as a whole has evolved over 4.5 billion years. A dedicated Saturn interior mission, a probe that descends into the atmosphere and measures composition, temperature, and pressure as a function of depth, analogous to the Galileo probe that entered Jupiter's atmosphere in 1995, has been proposed repeatedly by the planetary science community. The 2023 Planetary Science and Astrobiology Decadal Survey, the 10-year prioritization document produced by the National Academies of Sciences that guides NASA mission selection, ranked a Uranus orbiter and probe as the top priority for large planetary science missions in the coming decade. Saturn was not ranked first. The science community's attention, at this moment, has shifted toward the ice giants. Saturn, the most visually studied planet in the solar system after Earth itself, must wait its turn. That wait is not idle. The archive of Cassini data is still being worked. As of 2026, researchers continue to publish peer-reviewed papers drawing on measurements Cassini made between 2004 and 2017. The chronoseismology catalog, the mapping of Saturn's internal oscillation modes from ring wave patterns, is still being constructed. New wave structures in the rings are still being identified and matched to theoretical predictions. The grand finale gravity data continues to constrain interior models that grow more sophisticated with each iteration. A spacecraft that has been physically destroyed is still, in the form of its data archive, actively shaping scientific understanding. Saturn itself does not wait. The rings continue their measured disappearance. The helium continues its long infall through the planet's interior. The hexagonal storm at the North Pole continues its rotation, approximately one full revolution every 10 hours and 39 minutes by current measurements, though as established, that number carries a specific uncertainty. The great white spots will erupt again, on a schedule that the planet's internal thermodynamics dictates and that humans can roughly predict but not control. Titan's thick orange atmosphere continues to evolve, both from the energy deposited by Saturn's magnetosphere and from the slow organic chemistry driven by sunlight in its upper layers. Enceladus continues erupting from its south pole, feeding water ice into the E-ring, maintaining one of the most geologically active surfaces in the solar system on a moon that is only 500 kilometers in radius, small enough to fit within the borders of France. The scale disparity in this system is one of the things that makes it so difficult to hold in mind all at once. Enceladus, with its confirmed subsurface liquid water ocean, its active geysers, and its potential habitability, is 250 times smaller in diameter than Saturn itself. If Saturn were the size of a basketball, Enceladus would be approximately the size of a sesame seed with an ocean. The rings, stretching from 67,000 to nearly 500,000 kilometers from Saturn's center, if the faint outer rings are included, would span a distance on that basketball analogy that covers a dining table. The system is simultaneously intimate. The rings and moons interact gravitationally in ways that require precise calculation down to meters per second, and utterly immense. The human capacity to comprehend the system has been built incrementally by hundreds of scientists across multiple generations, using instruments that collectively represent the most complex technology our civilization has yet produced and launched away from Earth. Voyager 1 and Voyager 2 gave humanity its first detailed photographs of Saturn's rings in 1980 and 1981. Pioneer 11 arrived first in 1979, but with instruments too rudimentary to answer the questions the Voyagers later raised. Cassini spent 13 years systematically dismantling assumptions and replacing them with measurements. Each mission left behind a body of questions that its instruments could not answer, questions that only the next mission not yet built could address. This is the structure of knowledge about Saturn. It advances not linearly, but in discrete jumps, separated by decades of interplanetary travel time, each jump revealing a system more complex and more interconnected than the previous mission had shown. The pattern is consistent. Every time humanity looks at Saturn with better instruments, Saturn turns out to be stranger than the previous instruments suggested. There is no reason to expect this pattern to break. The rings will continue to fade on their 100-million-year timeline, indifferent to whether any instrument is watching. The helium rain will continue falling through the metallic hydrogen interior, releasing heat, depleting the outer layers, slowly but measurably changing the composition of the atmosphere that any future telescope or spacecraft will measure. The magnetic filtering layer will continue to present a perfectly symmetric face to the outside, concealing whatever asymmetric complexity exists below it. The planet vibrates. The rings record it. The record is only partially read. There is a specific quality to the kind of ignorance that Saturn currently represents in planetary science. It is not the ignorance of a problem that has barely been examined. It is the ignorance that follows deep examination, the kind that only emerges after you know enough to know precisely what you do not know. Before Cassini, the gaps in Saturn knowledge were poorly defined. After Cassini, they are sharp, specific, and quantified. The rotation rate is unknown within a range of minutes. The core boundary is diffuse within a radius range of thousands of kilometers. The ring age is uncertain within a range of hundreds of millions of years. The heating source for the thermosphere is unidentified, but its energy budget shortfall is measured. Precise ignorance is the closest thing science has to a map of what comes next. The pale yellow point of light that ancient Babylonian astronomers tracked across the sky, the slowest moving of all the visible planets, the one they associated with time and with the long turning of ages, turns out to have been changing all along. The rings they never knew existed were already falling. The helium was already raining. The interior was already vibrating at frequencies no instrument would detect for another 4,000 years. Saturn does not hold still. It never has. It is a system in motion, at every scale, from the microscopic ice grains spiraling into the atmosphere to the geological reshaping of its moons across billions of years. And at the edge of what is understood, in the territory that the next mission has not yet reached, the planet continues to change in ways that nobody right now fully knows.